Have you ever wondered how we discovered climate change? It all began in the early 19th century with the suspicion of ice ages and other natural changes in paleoclimate. The first inklings of what we now know as the greenhouse effect started to take shape. Joseph Fourier in 1824 proposed the idea, although it wasn't named as such at the time. His argument was further fortified by Claude Pouillet in 1827 and 1838. But it was Eunice Newton Foote who, in 1856, demonstrated a crucial piece of the puzzle. She showed that the sun's warming effect was greater for air filled with water vapor than for dry air. And guess what? The effect was even more pronounced with carbon dioxide in the mix. With these discoveries, the seeds of understanding climate change were sown. By the late 19th century, scientists began arguing that human emissions of greenhouse gases could alter Earth's energy balance and climate. The case for climate change took a leap forward when John Tyndall started measuring the infrared absorption and emission of various gases and vapors from 1859 onwards. Tyndall, an Irish physicist, discovered that the warming effect of our atmosphere was due to a very small proportion of its composition. While the main gases had little to no effect, it was the water vapor, along with trace amounts of hydrocarbons and carbon dioxide, that had a significant impact. His research laid the groundwork for future climate science. Fast forward to 1896, when a Swedish scientist, Svante Arrhenius, took Tyndall's discovery a step further. He quantified the effect of these gases and made the first quantitative prediction of global warming. Arrhenius hypothesized that if the amount of carbon dioxide in our atmosphere were to double, it would lead to a substantial increase in global temperatures. By the 1960s, the evidence for the warming effect of carbon dioxide gas had become increasingly convincing. By the 1970s, our scientific understanding of global warming had greatly increased. This era marked significant leaps in our comprehension of the role we humans were playing in the shifting climate narrative. Scientists made a startling discovery that human activities generating atmospheric aerosols, often referred to as air pollution, could also have cooling effects. This led to the concept of global dimming, a counterintuitive phenomenon where certain pollutants can actually reflect sunlight back into space, reducing the warming effect. Yet, the story of climate change is complex and multifaceted. Other theories were proposed for the causes of global warming, from the powerful forces of volcanism to the subtle variations in solar energy. Each theory added a piece to the puzzle, but none could singularly account for the changes we were observing. Fast forward to the 1990s, a pivotal decade in climate science. This was when the jigsaw pieces began to fit together more coherently. The accuracy of computer models improved dramatically, offering a more reliable window into the future. Observational work confirmed the Milankovitch theory of the ice ages, which postulated that shifts in Earth's orbit and axial tilt could lead to significant climate variations. A consensus position began to form. It became clear that greenhouse gases were not just minor players, but deeply involved in most climate changes. More alarmingly, human-caused emissions were not just contributing to, but were leading to discernible global warming. It was a realization that marked a turning point in our relationship with our planet. Since the 1990s, scientific research on climate change has expanded across multiple disciplines, deepening our understanding of causal relations, links with historic data, and abilities to measure and model climate change. Today, the study of climate change is not confined to the realm of meteorology or geology, but spans across biology, physics, sociology, and even economics. This holistic approach has allowed us to better comprehend the complexities of our changing climate and hopefully to better prepare for its future impacts.